Josh, go ahead and take it away.
Great, thank you for the introduction, and thank you all for being here. Let me just get my screen set up here. All right, is that looking good?
Looks great.
Okay, great. Yeah, so this talk will be kind of a mixture of exoplanet and solar system science, using coupled atmosphere-interior-redox models to predict terrestrial planet atmospheric evolution and anticipate biosignature false positives. So this work is done in collaboration with colleagues at UC Santa Cruz, my postdoc mentor Jonathan Fortney, as well as Francis Nimmo, who helped with a lot of the interior modeling, as well as the contributions of several talented students, Max Galloway, Maggie Thompson, and Nick Wogan at UW. I think is on the call, so he can answer any difficult questions about the outgassing stuff. So all of this is motivated by the expectation that very soon capabilities to characterize terrestrial planets will improve dramatically, and I'm sure I don't need to convince you of this. There's been a lot of interesting work coming out of Goddard on this subject, looking at different scenarios for, say, the TRAPPIST planets and what molecules may or may not be detectable and not be detectable. Sorry? Thanks. Yes, there's been work done here on how Webb may be able to characterize terrestrial planets, and of course there's analogous work in looking at what might be possible with the ground-based ELTs in terms of detecting molecular detections with high-resolution spectroscopy. And then, of course, looking further ahead, well, sometime in the next few months, I expect we'll know the outcome of the Decadal Survey, which could prioritize flagship mission concepts purpose-built to characterize terrestrial planets and potentially look for biosignature gases in some detail. So this is also on the horizon. So with that, in the future, what I want to convince you of today is that we really need sort of testable and ultimately tested theories of rocky planet evolution to understand these objects and be able to distinguish lifeless planets from genuinely inhabited worlds. And so with that theme in mind, today's talk has kind of got three distinct parts to it. The first will be looking at oxygen biosignatures as a case study in the ways in which understanding whole planet evolution can be really helpful here. Next, we'll talk about what we can learn about Venus as an analog for kind of highly irradiated terrestrial planets and what future missions to Venus could teach us. And then, time permitting, I'll talk a little bit about methane as a biosignature. Just to give you some sense of the time horizon, the first part of the talk is mostly going to be relevant to kind of next generation Louvois-Habex observations. The Venus stuff is more relevant to kind of end of decade solar system missions, and then the methane biosignature work is really relevant to kind of next year Webb observations. I'll break between the sections for questions, but do feel free to jump in anytime if you have a burning question or if something isn't clear. So just to remind you why we think oxygen is a potentially very good biosignature. The argument for oxygen is more than just an argument by analogy. It's not just that, well, Earth life makes oxygen, and therefore we look for oxygen. I think you can make a fairly compelling argument on the basis of the evolutionary payoff that any organism which develops oxygenic photosynthesis will have compared to other forms of photosynthesis or other metabolisms that are limited by the substrates available. It's also generally been thought to be difficult to maintain oxygen-rich atmospheres through purely lifeless geochemistry. With that said, there is a growing literature now on all the hypothetical scenarios through which you might be able to build up oxygen without life. And there's review papers on this topic, kind of going through these different scenarios and how you might distinguish them from genuine biological oxygen. For the most part, though, these scenarios are most applicable to planets around low mass stars owing to their stellar spectra and also the stellar evolution trajectory that just makes non-biological oxygen buildup more probable. What I was interested in instead was kind of the general tendency of rocky planets to oxygenate their atmospheres, regardless of what the star was doing. And so to tackle this, I developed and applied this whole planet evolution model to try and anticipate oxygen buildup. And so what this model attempts to do is sort of self-consistently treat planetary evolution from magma ocean origins through to more temperate geochemical cycling. And so you can potentially oxidize your planet through dissociating water, preferentially losing the hydrogen to space, and that oxygen that's left behind can either sit in the atmosphere or be sequestered in the interior. And this process continues as the planet cools off, except now, after the magma ocean, you've got all these crustal sinks of oxygen to draw down any oxygen you make through hydrogen loss. To do this self-consistently, you need to track the interior evolution of the planet, because of course, these crustal sinks are going to depend on things like the melt production of the planet, and so you need an interior model parameterizing mantle convection, magma ocean convection. You also need to keep track of the climate of the planet with a radiative convective model, since climate controls a lot of these crustal processes. But then if you want to know the climate of the planet, you need to know where the volatiles are, and so it's important to track fluxes of water and CO2 between the atmosphere and the interior. So I've tried to tie all this together in a self-consistent way, and this model has a heritage in other attempts to do this kind of whole planet redox evolution. You can see why I've called it the Pac-Man model. It's a bit of a forced acronym, but I think it works. And the code is available if you want to play around with it. One other thing about the model, as you can imagine, when you're trying to model whole planets in this way, you have to make a lot of simplifications. There are a lot of unknown parameters, not just the initial conditions, but also, how is the star evolving? How does the carbon cycle work? How do these different crustal sinks work? And so I've tried to kind of Monte Carlo over all of this uncertainty. And so when you see results from the model, they'll be presented as like confidence intervals with some shaded region and a median to try and encompass this range of parameter values and feedbacks and so on. So to start off with, we applied the model just to Earth through time. This is a model applied to a lifeless Earth, right? Because we're interested in non-biological oxygen buildup. And there's a lot going on in this figure, but I'll walk you through it. Every subplot here is a time evolution plot on the x-axis. So this is time in years advancing logarithmically from magma ocean origins through to 4.5 billion years later. And we're plotting the time evolution of both atmosphere and interior variables. So we'll start with, and you can see, of course, that there are large confidence intervals for these things because of all the uncertainties in the various component models. So we'll start with the thermal evolution. This is the evolution of the temperature of the mantle and the surface over time. So you can see the magma ocean freezing here after a few million years. The surface temperature drops. You can see this more clearly in the second plot, which shows you the evolution of the solidification radius from the core mantle boundary to the surface as the planet cools. And then the whole time the atmosphere is co-evolving with this interior evolution. So we're tracking atmospheric water vapor, carbon dioxide, and oxygen. A lot of this behavior is driven by the planet's energy budget shown here. And so this plot is showing you the outgoing long wave radiation, obviously very high when your planet is molten, but then as it cools off and eventually drops below the runaway greenhouse limit after a few million years, this is when a lot of things happen all at once. This is when your magma ocean finally freezes. This is when your catastrophically degassed steam atmosphere condenses out as liquid water on the surface. So you see the blue here, the water vapor drops, at the same time as liquid water on the surface goes from nothing to a few kilometers, globally averaged ocean depth. Once you've got liquid water around, you can have a temperate carbon cycle. You can have the weathering of silicates drawing down carbon dioxide. Of course, crustal production, melt production is driving a lot of these, driving the carbon cycle and the oxygen sinks. And so crucially, the whole time you're keeping track of the redox evolution of both the mantle, the interior, and of the atmosphere, keeping track of fluxes of oxygen in and out of the atmosphere to try and anticipate whether or not oxygen could build up non-biologically. And so what you find is for this lifeless Earth scenario, you always get the same answer, in the sense that after 4.5 billion years, the oxygen here, shown in green, is always basically zero. It reliably predicts an anoxic atmosphere without life on Earth. And so this is good news for oxygen as a biosignature, right? It tells you if you have a literal Earth twin, then it doesn't seem likely that you're going to get an oxygen-rich atmosphere without life. The bad news is, though, when we change the initial conditions a little bit, so repeat those calculations, Earth-sized planet around a sun-like star, but change the initial volatile inventories that the planet is endowed with. And so when you do that, we find there are 3 distinct scenarios through which you could potentially build up a lot of oxygen without life. And in the interest of time, I'll just go through one of them, the water world scenario, to give you a sense of how this works. So this is the exact same calculation that I showed you before, Earth-sized planet around the sun, except now we are endowing our planet with an initial water inventory of tens to hundreds of Earth oceans. And so now when the magma ocean freezes after a few million years and the steam atmosphere condenses out, you're left with potentially hundreds of kilometers of oceans at the surface. And so this very deep surface ocean exerts a very large pressure on the silicates below, which increases the solidus, the melting point of rock. And so the effect of this is to pretty rapidly shut down the production of new crust, shut down melt production. And this effect has been described previously in other kind of geodynamical studies. But the consequences of this, for the redox evolution, is that if you shut down new crustal production, you shut down all your oxygen sinks. And so what you find is that over billions of years, a very small leakage of hydrogen to space is potentially enough to build a very oxygen-rich atmosphere, as you see in the atmospheric evolution here. Oxygen in green is increasing over several gigayear. And you can see this behavior more clearly in, that's the whole thing again. You can see this more clearly in this subplot, where we're showing final oxygen after 4.5 billion years as a function of how much water you started with in Earth oceans. So you can see very clearly, every dot is a model run, as you increase that initial inventory above a few tens of Earth oceans, you start to get a lot more model runs where oxygen buildup is happening. And so in the paper in this, we try and discuss how you would distinguish this observationally from planets that were planets with genuine biological oxygen. And the key in this particular scenario is to find some continents, right? Because if you can detect any kind of land through an ocean continent dichotomy, then that immediately puts a constraint on the maximum depth of the ocean that would kind of rule out these sorts of inventories. And so there are a number of observational strategies you could try and use to do this, in particular using time resolved photometry to back out the surface dichotomy is probably the most promising. What you can do though with a model like this is ask more general questions about what are the astrophysical parameters that make non-biological oxygen buildup more likely, and so you can formulate kind of a testable hypothesis like that. This movie was done by a recent Santa Cruz graduate, Max Galloway, who's just starting at UCF, the graduate school. We've got an ensemble of planets here, and we're showing their time evolution. This is time, bottom left, of atmospheric CO2, oxygen, and water vapor. The color is the surface temperature. And then we're plotting, these are planets with just different planet-star separations. And so you can see, this is the runaway greenhouse limit here, the dashed line evolving as the star is getting brighter. So you can start to make some, you can start to formulate some population level hypotheses about at what planet-star separations is oxygen buildup more probable. This is work in progress. So just to wrap up the oxygen work then, I realize I haven't gone through all 3 scenarios, but I've hopefully convinced you that it's at least plausible that you might get non-biological oxygen buildup on habitable zone planets around sun-like stars. Unfortunately, we think that there are observations you can make to discriminate this from biological oxygen, and there's sort of ongoing work to figure out what would be needed specifically in terms of observational capabilities to do that. Any questions on the oxygen stuff before I move on to part 2?
So it looks like we have a hand up by Ravi. Do you want to go ahead and ask?
Hey, Josh, thanks. If you go back to your simulations, the slide before, so the end of the simulations, it looks like all the planets are hot.
Right, so we're extrapolating into the future. So this, I think it goes out to 7 billion years for solar evolution. So towards the end, everything's going into runaway greenhouse.
Right. So essentially, are you saying that most of the planets that have abiotic oxygen buildup are runaway greenhouse planets?
Well, so if you look here, you can certainly see interior to the habitable zone, there seems to be a lot more oxygen buildup, but there is a significant population of planets where oxygen is building up inside the habitable zone due to some combination of the 3 scenarios that I mentioned earlier. But yeah, there is a very large population of oxygen buildup interior to the habitable zone as you go into runaway greenhouse. We'll talk about that with the Venus stuff as well.
Okay, yeah, thanks.
Any other questions right now? All right, so actually Ravi's question is a nice lead into what we're going to discuss next. So this is just freezing the movie at 4.5 billion years. And if you do that and you look at Venus-like planet-star separations, you see an interesting population of planets here. You see planets that look a lot like Venus, that they have virtually no oxygen in their atmospheres, virtually no water vapor in their atmospheres, entirely desiccated. But you also see this population of planets at Venus distances that are nothing like Venus. They have a lot of oxygen in their atmospheres or a lot of water vapor or both. And so it's a really interesting question as to why Venus looks like it does and not like one of these other seemingly self-consistent outcomes. Right? So I think for that reason, understanding Venus is a really critical component to understanding oxygen as a biosignature and its potential false positives. Is there another question there, Vlad?
Yeah, Vlad, if you do want to.
Yes. Hello, Joshua. Yeah. So the question is that in this models, do you use the G-type stars only, or variety of spectral classes for the spectral distribution?
Everything I've showed you so far is for G-type star, and actually I think everything in this talk is basically for G stars. Yeah. But I am looking at applying it to low mass stars as well.
Thank you.
Josh, can I quickly interrupt? Sorry.
Yeah, go ahead.
So I see that you have not Venus-like simulations here. Do you mean not current Venus-like? Because
Yeah, basically they are terrestrial planets at Venus-like separations, but their atmospheres look nothing like modern Venus. They have either a lot of oxygen in them or a lot of water vapor, whereas of course Venus is just a CO2-dominated atmosphere. So that's
right. So the
kind of
current
starting.
Venus, not current Venus-like one, because the
Right.
Venus evolution had a different. So
Yeah, so this is we'll talk about Venus evolution in a second, but I also just wanted to motivate the Venus work, as well as being interesting to kind of exovenus analogs. There's some intrinsically interesting questions surrounding Venus. In particular, was it ever habitable in the past? There's a recent GCM studies showing that due to Venus's slow rotation, you can potentially have maintained a habitable climate until relatively recently due to cloudiness at the subsolar point. We've also known for quite a while there are these old tessera regions on the surface of Venus, the oldest part of the crust. There's tentative evidence that it could be felsic. Additionally, there's geomorphological evidence of these old regions from radar imagery, arguing that some of the features we see are consistent with past water erosion, fluvial erosion. With that said, there's other possible explanations for this, and a recently habitable Venus is always been difficult to reconcile with the fact that if you believe you've lost the water recently, lost the hydrogen recently, where did the oxygen go? How do you reconcile a recently habitable Venus with the fact that there seems to be no leftover oxygen in Venus's current atmosphere? And so with all of this in mind, I thought we could apply our model to Venus to try and say something about the relative likelihood of past habitability or not, and to potentially say something about expected exovenus analog populations. So this is the model applied to Venus. It's essentially the same model as before, except I've added a few bells and whistles. There's a stagnant lid model in there now, a transition from plate tectonics to stagnant lid, sort of full generality in the internal evolution. We've also added trace gases, argon-40 and helium. These are basically markers of outgassing. So argon-40 being a potassium-40 decay product. Once you degas that argon, it's presumed to just sit in the atmosphere forever. So the amount of argon that's sitting in Venus's atmosphere is kind of a measure of the cumulative outgassing of Venus's history. And so we want to make sure our model can recover that. Helium's similar, it's a uranium and thorium decay product. But in the case of helium, it doesn't sit there forever. It does get lost to space on 100 million year timescales. And so the amount of helium in the atmosphere is thought to be a marker of more recent outgassing. So we want to make sure our model can recover that as well. And so broadly speaking, the model can get you to modern Venus. So you can have a temperature evolution that gets you to the modern surface temperature. Skip over that. You can recover the modern atmosphere. That is, after 4.5 billion years, you can be left with a dense CO2 atmosphere with negligible water vapor or molecular oxygen. You can recover, right here, you can recover the modern estimates of the modern heat flow from the interior. I'm just going to not go through all these in detail. And you can roughly recover the correct amount of argon-40 and helium. Now, all the model runs in this figure that I'm showing you here. You will have noticed never had past habitability, right? Ocean depth was always zero. The surface temperature, as shown by this thermal evolution in the top left, just goes straight from magma ocean to modern Venus-like temperatures. But this isn't the whole class of solution. In fact, you find that if you break down all the model runs that get you to the right answer, that get you to modern Venus, you find they fall into these two classes, the ones that I'm showing you here, where Venus was never habitable, and these ones where you had 100 meters-ish of global oceans of order a few billion years before going back into runaway greenhouse and losing all your water. And so you can see that in the temperature evolution here, where you drop into a habitable state for a time before going back into moist then runaway greenhouse and losing the water. You can see that in the atmosphere evolution here as well, where CO2 is drawn down for a time and you go back, losing your water, losing your oxygen. But these habitable scenarios can also recover the same amount of argon-40 and helium and recover all the other modern constraints. And so that's just showing you them recovering the constraints of modern Venus. And here they are side by side, those two scenarios, one in which Venus was never habitable, went straight into runaway, another where you have transient habitability and an ocean depth of about 100 meters. So now that you have these results, you can do science with it, right? You can ask the question, well, what must be true of the underlying parameters to give you these scenarios? What is controlling which of these occurs? And sorry, this is a very busy plot, but it's we'll just go through some of it. But this is an attempt to kind of break down what is controlling whether or not Venus was habitable in the past. So every dot here is a model run. The yellow dots are model runs that get you to the right answer, that get you to the correct modern Venus state, but were habitable for a time. The purple dots get you to the correct modern Venus state, but were never habitable. They were just always surface temperature of 700 degrees. And then the cyan dots are all the other model runs that don't get you the right answer, which is to say that after 4.5 billion years, they don't look like Venus. They have too much oxygen around or too much water vapor around and so on. So some of these relationships are quite intuitive. This is just plotting the albedo, which is a free parameter in our model, against how much water you start with, and then showing the distribution of these three types of model runs within that. And so, of course, to make a habitable Venus work, you had to have had a high albedo, higher than 0.4. Otherwise, you're just straight into runaway, right? So that makes sense. Additionally, there's a negative correlation between how much water you started with and the albedo. And this kind of makes sense too, in that if you started with a lot of water, your albedo can't have been that high because you must have gone into runaway greenhouse long enough ago to have had enough time to get rid of all the water since. You can also see that in this subplot, which is showing you albedo versus kind of the maximum ocean depth. Obviously, the never habitable runs never had an ocean, so that's always 0. But with the yellow dots, you see this negative correlation again. Larger max ocean depths require smaller albedos to have had enough time to get rid of all that water since the planet went back into runaway greenhouse. You can put some rough constraints on the initial inventories. This is kind of an interesting one. So this is plotting final oxygen after 4.5 billion years as a function of this dry crustal oxidation efficiency. And so this parameter is kind of like a fudge factor for the efficiency of all the other oxygen sinks that aren't outgassing or water rock reactions. So this could include the efficiency of direct dissolution of oxygen into surface lavas. It could involve direct gas phase grain interactions. It could involve oxidation of aerosols from explosive volcanism. It could involve like supercritical reactions between the atmosphere and the surface. Whatever this sink is, you find that it has to be relatively efficient. That if you make it inefficient, then you always have too much oxygen left over, and you don't get to this state where you have an oxygen-free modern Venus. This figure is kind of relevant for the exoplanet analogs. This is just showing you different outcomes: final water vapor, final CO2 after 4.5 billion years. So in addition to the population of planets that look like modern Venus, you have some that never got rid of all their water vapor, their thick steam atmospheres. You have some that remained habitable. So it'll be interesting to kind of test to what extent this possible diversity of Venus outcomes is represented in the an exo-Venus population that is soon to be characterized. And then finally, this is telling you something about how escape works. So I should say that the way that the model treats atmospheric escape is very simple. I'm not trying to explicitly calculate the radiative equilibrium of the upper atmosphere. I'm just assuming some isothermal temperature of the upper atmosphere. And then sampling that. And you see here that it only really works, you only really get modern Venus when that temperature is relatively warm. And so I thought it'd be worth looking into this in more detail. There is literature on the ways in which having a very CO2-rich upper atmosphere cools the upper atmosphere and therefore throttles the amount of water vapor that can get to altitudes where it can escape. Just because it's so cold, it condenses out at lower altitudes. And so I was curious to see what would happen if I put this feedback into the model, and I did this in the crudest possible way, just saying, okay, the temperature of the upper atmosphere depends on how much CO2 is around, but just do a sensitivity test like that. And what you find is that when you implement this, it's virtually impossible to recover modern Venus without a habitable epoch at some point in the past. And the reason for that is that when you're habitable, you can draw down CO2, transition to a nitrogen-dominated atmosphere for a time, a much warmer upper atmosphere, where it's much easier to get rid of the water vapor and lose it to space. Whereas if it's always been CO2-dominated, it's always been a cold upper atmosphere, and it's very difficult to lose all the water. And you can see that in this movie, where, again, we're just looking at a population of model outcomes. The squares are the ones that get you to modern Venus and we're habitable, and then the dots are planets that don't recover the modern state. We're plotting water vapor in the atmosphere, CO2, and oxygen is the color now. This is time evolving in the bottom left. So you'll see these habitable ones, their CO2 gets drawn down when they drop out of Runaway Greenhouse. This increases the temperature of the upper atmosphere and allows them to lose water more easily as they go back into moist greenhouse and Runaway Greenhouse and eventually get to something looking like modern Venus state, as opposed to these dots up here. They never go through a habitable epoch, and so it's very difficult for them to get rid of all their water vapor. Just let this finish. You have this population of squares here that gets you the correct modern state. I want to emphasize there's a lot of caveats on this. I'm only really considering water as the species that you lose hydrogen through. In practice, you could imagine if there's a lot of molecular hydrogen or methane around, it wouldn't be cold trapped in this way. And people have argued that maybe the initial atmosphere of Venus was in fact a CO hydrogen dominated atmosphere, which would totally change the escape regime. It could potentially allow you to get rid of your hydrogen more readily. Or maybe you had a large impact that converted all the water to methane for a while, and you lost the hydrogen that way. So certainly more comprehensive models are required to look at these different possibilities in more detail. But taking that at face value, some possible implications for future missions. And I guess I want to emphasize here that while I think this modeling work is interesting, there's certainly not going to be a definitive answer on past habitability without further constraints on Venus's evolution. So certainly measurements of D to H ratio, xenon isotopes, and better constraints on helium would help constrain this whole atmospheric evolution framework more rigorously. Additionally, something that's kind of interesting that falls out of the habitable scenarios is that if you believe that Venus had a 100-meter global ocean for a billion years, and that had a comparable saltiness to Earth. When you lose that water and evaporate that ocean, all that salt, those evaporites, should have been left behind, and they should not have been destroyed by the subsequent climate evolution. It never gets hot enough to really decompose these. And so the size of these deposits should be comparable to Earth's evaporite deposits, which is something you could potentially look for with remote sensing. And of course, there are many other geomorphological or mineralogical lines of evidence you could try and make for hydration, for past hydration, or fluvial erosion. Fortunately, there are upcoming missions coming up, as you will know. The better constraints on gas abundances and isotopes from Da Vinci Plus will be very helpful. High resolution images of the old tessera terrain as it descends through the atmosphere. This could potentially be definitive if you see very clear evidence of past fluvial erosion in the geomorphology. And then the orbiters, both Veritas and the Envision European orbiter, will constrain the interior state through improved radar imagery and be able to say something more definitive about the tectonic evolution. So to wrap up the Venus work then, the main point I really want to make here is that both transient habitability and never habitable histories can be reconciled with everything we know about modern Venus, the bulk atmospheric composition, the trace gases that are markers of outgassing, the heat flow, and so on. Both of those scenarios can be made to work. If you believe that having a really CO2-rich atmosphere throttles water loss, then transient habitability is favored, but there are a lot of caveats on this. And so really, understanding why Venus's atmosphere is oxygen-free is going to need future in situ missions, and this is going to be really important for interpreting potential oxygen detections or lack thereof on terrestrial exoplanets. So that's the end of the Venus section. Are there any questions or comments on that before I move on?
So it looks like Vlad has a question.
Yeah, go ahead.
Yeah, hello, Joshua, again. So, yeah, I have two questions. The one, it's about, have you looked at the fate of nitrogen? So the nitrogen is probably one of the key species, right, in the atmosphere that can offer, this the opportunity to look into possible scenarios of atmospheric evolution, because it has awfully lot of molecular nitrogen, 3 times as today's Earth in kilograms, and even though a lot of it escaped over the 4.5 billion years, still have a lot of it, which tells us probably that it comes from tectonic activity, right? And tectonic activity was important on early Venus, and also the tectonic activity is also driven by the water reservoir, right? So that tells us something about the oxidation of the upper mantle. So that's the first question. What do you think?
Yeah, that's a good question. The reviewer also had a lot of questions about how nitrogen works in our model. We did not try to put in an explicit nitrogen cycle to try and sort of couple nitrogen outgassing to the interior redox state. That was just too much complexity for this calculation. But what we did try and do is say, well, what is the sensitivity of our results to different background nitrogen inventories? And so I can maybe if I can quickly skip ahead to this slide. We did this. Oh yeah, here it is. Okay, so this is it's really hard to know, right? If it was habitable for a time, would you draw down that nitrogen and store it in clays and subduct it, or has there just always been a 3-bar inventory that was degassed from the start and just always been there? And so we looked at those two, those N members of different nitrogen backgrounds, and it doesn't really affect the never habitable scenarios very much, right? If you've always just had 90 bars CO2, whether or not you have half a bar or 3 bar of nitrogen in the background, it doesn't matter. But it does matter a lot for the if you had transient habitability, because of course, if you have less nitrogen, if the nitrogen gets drawn down, then it's a lot easier to lose the water vapor. There's less of a cold trap. And so we did find that the more that nitrogen was drawn down, kind of the more frequent these habitable past Venus scenarios became, whereas they're less frequent if you just always had 3 bar nitrogen. But it's a relatively subtle effect. It's, you know, sort of 30% more likely or less likely. So that's what we looked at with nitrogen, just a kind of sensitivity test.
Yeah, thanks. And the second one, it's about carbon dioxide. Yeah, so the carbon dioxide cooling efficiency, you know, the mostly the one of the highest in the at about like 100 kilometers in the thermosphere, at least in the current Earth. Every time that we have you know, big solar flares in Earth atmosphere, we have the so-called supercooling effects when the temperature of the thermosphere goes down simply because of the radiative cooling of carbon dioxide at 15 microns. So yeah, and this effect is important. But when you go up, you know, above the exabase, above like you know 200-300 kilometers above the ground, most of the CO2 is fossilized. So the you have mostly CO, which is not a very efficient cooler. So that's the one thing to, you know. So it's not only not always the cooler when we're talking about the initiation of the atmospheric escape. And the second question for the habitability of CO2 is that if the CO2 is really, you know, was abundant, then it would you know, increase the acidity in oceans, which make prebiotic chemistry reactions were very slow, if not impossible. So that the CO2 is good, might be for those processes, atmospherically speaking, but bad for habitability in terms of forming biological molecules.
Oh yeah, that's interesting. Thank you. I would love to kind of couple this to a more complete model of the radiative transfer in the upper atmosphere. My thinking was that the water vapor is going to be limited by kind of the minimum temperature in the atmosphere. Even if it heats up as you go higher up, the water vapor will be throttled through that coldest point. But yeah, certainly, yeah, this definitely requires more detailed modeling. And yeah, the point about pH and habitability is interesting. I haven't considered that.
Yeah, well, maybe we can talk about that later. Yeah, so I'm looking at this question right now. So it's yeah, you need probably some kind of sweet spot of that. So of CO2 in order to satisfy both criteria.
Any
Thanks.
other Venus questions or comments? All right, well, in the 15 minutes or so we have left, I wanted to change course a little bit and talk about another biosignature that I think is potentially, there's more of an urgent need to understand it than for oxygen. That is methane as a biosignature. So in the past, I've done work arguing that methane, biological levels of methane on terrestrial planets are sort of imminently detectable. It's just something you could do with Webb for the TRAPPIST planets in, you know, I order 10 transits to do that methane detection. And you don't have to take my word for it. There's other, you know, simulated observation studies that have come to sort of similar conclusions. In fact, methane is so detectable that there are already claims. Oh, actually, sorry, before I get into that, I want to just say something why methane is a promising biosignature. Again, there's an evolutionary imperative for life that makes methane, in the sense that the substrates you need, CO2 and hydrogen, are probably ubiquitous. There's reason to think that methane making life evolved very early in Earth's evolution. And as I've said, this is far easier. It's far easier to take biological levels of methane than it is to detect biological levels of oxygen with Webb. So easy, in fact, that there are already claims of methane detections in terrestrial planet atmospheres. So this is HST spectroscopy of GJ1132b, this paper that came out this year, claiming for making claims of detecting both methane and HCN in this secondary hydrogen-dominated atmosphere. And so there are a number of kind of theoretical problems with this. To make this scenario work, they need to invoke a really reducing mantle. And so you can do calculations to show, and this is work done by Maggie Thompson, a Santa Cruz graduate student, basically calculating how carbon speciates as a function of the interior redox state. And what you find is that if you melt rock that's just as reducing as has been claimed, the GJ1132b, basically every atom of carbon should be precipitating out as graphite and not be in gaseous phases. It's very difficult to make anything, to make gaseous methane under those conditions. And there have been other studies that have looked at the same HST data and said it's consistent with a flat spectrum. But the point is, the fact that people are already making these claims of methane detection with HST makes me think that it's certainly going to happen more with Webb. The problem is, unlike for oxygen, where there are attempts to kind of think about oxygen in a whole planet evolution context, there's no equivalent Pac-Man model for methane. There isn't that kind of whole planet understanding of when methane is likely to accumulate with and without biology and so on. And so something we've been working on is to try and, at least as a starting point for this work, is to kind of think about all the plausible scenarios where you might be able to make a lot of methane without life, and then what would be the contextual clues for those scenarios that would alert you to the fact that it was potentially non-biological methane, like it was outgassed, what the other species that came along with that, it was a very icy body, what would you expect to see, and so on. So this is ongoing work and potentially relevant in the area of Webb, where methane detections for terrestrial planets are going to be quite feasible. So just to wrap up then, I've tried to argue that the search for life on exoplanets is really inseparable from attempts to understand the lifeless evolution of rocky planets. And so building models to kind of couple atmosphere interior processes and formulate testable hypotheses on how these uninhabited worlds work is going to be really important. Oxygen is the best understood in this regard, but there are still a lot of things we don't know. And so returning to Venus, as well as Webb observations of really highly irradiated terrestrial planets, are going to greatly advance our understanding of oxygen buildup without life. And I hope that a similar kind of whole planet approach can be taken for methane biosignatures, although in this area, our understanding of planetary processes is lagging way behind observational capabilities. So there's certainly need to further work on that. So that's everything I had, and yeah, plenty of time for more questions on anything I've talked about.
Thanks, Joshua. A lot of really, really interesting stuff. So I see Richard Gordon, you have a question here. Do you want to pop on and ask him it, or I can also go ahead and just read it off? Okay, I'll go ahead and read it. So, so yes, what is the probability of getting the amount of water consistent with continents? I'm guessing this is probably on the Venus, the earlier simulations, the first two portions.
So I would say that what determines like exposed continents and continental area is kind of an unsolved problem. So the way that I have tried to deal with it is just putting in a very kind of crude, deep hydrological cycle with, some rate of return of oxygen through subduction balanced by water outgassing, and it comes to some steady state. And I've just assumed some Earth-like hypsometric curve for the sort of height distribution of the continents. So, and then the initial water inventory is anyone's guess, right? So I'm just sampling over a very broad range of initial water inventories for the Earth and Venus, like calculations that I showed. So, yeah, I guess I'm not sort of explicitly trying to solve that problem. The model is just keeping track of, in a very crude sense, like, is there continents or not? Is there so much water that continents are an impossibility, or is there, an amount of water that's consistent with some amount of land? So, yeah, sorry if that's not a very satisfying answer, but it's difficult to parameterize kind of an unsolved problem.
Additional questions? I have a couple, Joshua, but I'm going to hold them off until other folks get a chance. I'll go ahead and shoot one. So just a broad one for that early coupled model for the oxygen. Is there a way that you could have an impulse like an impact that I think, maybe people do expect Venus experienced an impact, or the Earth certainly, experienced an impact early in its history? Is there a way that you can actually modify some of the evolution, the interior atmospheric evolution?
Yeah, this is something that I want to try. I've been thinking about how to inject giant impacts to see how that affects the subsequent evolution. I mean, the interior evolution is sort of a simple parameterized convection model, right? So it's not like I'm resolving the convection and we'd be able to dynamically resolve how that is affected by an impact. But you could certainly look at how that sudden heat injection, delivery of volatiles, delivery of reducing material affected the subsequent evolution. Something I have looked at is just imposing kind of estimates of material delivery through the Hadean, the early Archean, reducing material to see how that affects the likelihood of oxygen buildup. It doesn't have a large effect on most of the scenarios, just because the oxygen buildup happens later, billions of years later. And so it doesn't really matter if you sprinkle on a bit of reducing stuff early on. But it does affect the scenarios where the model predicts you're left with oxygen after the magma ocean is formed, because if you're suddenly, you're hitting the planet with all these reduced rocks at that time, there isn't the opportunity for that oxygen buildup.
If there's not another question, I don't see any right now, I'll ask for the methane portion. So one of the things, because this is kind of larger time steps at capturing evolution, because the observations are ahead and we actually might be able to get pretty good SNR detections of methane, is there anything that has been done to quantify methane variability on these types of planets because of like cyclical, shorter term changes? Like you can imagine like partial glaciation, all those other types of things that might be affecting methane variability.
I'm sure there are, but nothing really comes to mind. I don't think there's a lot of work on kind of looking at that parameter space and how methane might vary. I think there's some consideration of like methane seasonality. I mean, there is some methane seasonality on Earth. Mostly that's non-biological. It's just how the photochemistry changes. Like Stephanie Olson has a paper on that. In anoxic atmospheres, which is kind of what we would be interested in for methane as a biosignature, the photochemical lifetime of methane is fairly long, right? It's like potentially tens of thousands of years. And so I wouldn't necessarily expect a lot of year-to-year variation in that case, just because of the long lifetime, as opposed to the oxidized Earth, where the photochemical lifetime is very short. And so the potential for that kind of variability is elevated.
Yeah, I think I'm thinking more like orbital, rotational variability and kind of effect, maybe on like a slightly longer time scale, but kind of a medium time scale relative to the long-term stuff. But yeah, I mean, sounds like additional interesting papers to be, written on it. Any more questions? If not, what you can do is if you have questions that do pop up, because there's a lot of cool stuff Joshua just covered here, I can pass on his email address, and I'm sure he'll love answering it in, big blocks of text. So Joshua, thank you for a really interesting talk on a couple different topics related to Venus and exoplanets. And I think it gives a lot of people things to chew on. So Thanks
so much for having me and for the great questions. This is fun.